afternoon, everybody. My name is Jackie, and these are my teammates, Navy, Maggie, Tiffany, and Carter, and our project is called Innovative Design and Substation Engineering. Today we're going to be talking to you about electrical substations, the technology behind them, and the many issues surrounding them. We're also going to talk about why exactly they're so important to the community. We're finally going to talk about our solution, and especially the environmental aspects of it. Then we're going to explain to you where this project should go should it continue in the future.
We see these enormous systems occupying land in our communities all the time. As unpleasant as it may be to see these structures in your neighborhood, substations are vital to leading a comfortable life in society. They're responsible for the transmission and distribution of electricity throughout the community, as well as the alteration of voltage levels of this incoming power. Despite the crucial role these systems have, they provoke a general discontent amongst the community due to their excessive spatial requirements, poor guard against weather, and poor aesthetic appeal. These weaknesses demand an urban solution to the problem at hand. Substations have three basic components. First, the bus systems, which regulate the flow of electricity through the use of circuit breakers and disconnects. Second, transformers, which step down the voltage levels. And finally, the feeder rows, which contain the separated voltage levels to be distributed to the final destinations.
Redundancy is very important to substation design. Redundancy allows one or more lines in the station to fail without impacting the station's performance. There are three main levels of redundancy: N-0, N-1, and N-2. N-0 provides no redundancy whatsoever. If a line fails, it is out and no longer functions. N-1 is the most common form of redundancy, allowing one line to fail and the station can still function as normal. It is most commonly used in residential and business settings. The rarest form of redundancy is N-2. N-2 allows for two lines to fail and the station can still function as normal. It is reserved for areas where power is very crucial, such as airports, hospitals, and government buildings.
Redundancy plays an evident role in the configuration of bus systems. As mentioned earlier, bus systems direct and control the flow of electricity throughout the substation. However, this simple task can vary in its reliability due to specific design choices that are made. In the straight bus design, circuit breakers are aligned in a series, in a straight chain. This means if one breaker were to fail, the entire system would collapse in this N-0 design. The sectionalized bus adds an improvement to this design by adding an additional breaker connecting two of these straight chains. This provides an additional route of flow for the electricity in case a single breaker were to fail in the N-1 design. And finally, the breaker and a half system shows the N-2 design by distributing 3 breakers for every 2 transmission lines. In this design, the system would still function despite the failure of any 2 components. For our particular project, we implemented the breaker and a half system in order to have the greatest amount of reliability, given that we'd be supplying to both the airport and the local community.
One of the most important advancements in modern substation technology has been gas-insulated switchgear. Traditional substations are air-insulated, meaning that the wires must be spread a far distance apart so that electricity cannot jump from wire to wire. With gas-insulated switchgear, the conductive material is placed inside a pipe insulated with sulfur hexafluoride gas and nitrogen gas. This gas acts as an insulator and allows the pipes to be placed very close together. This dramatically shrinks the size of the substation. In addition, gas-insulated switchgear is safer than air-insulated because there's no possibility of electricity jumping from wire to wire. An even newer technology is gas-insulated transformers. Traditional transformers are filled with oil. This can be dangerous because oil can leak out of the transformers and cause explosions or fires. In addition, to move an oil-insulated transformer, all the oil must be drained out, the transformer must be moved, and then the oil must all be placed back in. This is a lengthy and costly process. Gas-insulated transformers solve all these problems.
Our mentors assigned us the task of solving all of these problems in an urban environment. We selected Newark, New Jersey since it's so close to home. We were instructed to place our station near the airport, meaning we were required to use an N-2 design. In the wake of storms like Hurricane Sandy, we wanted to be especially careful about the flooding issues of the project. Lastly, though we were given a very specific location, we wanted to make sure we utilized concepts that could be taken across the board into many different locations. Our solution is to first off shrink the station down using the gas-insulated technology that Maggie spoke about. Second off, we plan to place the station in the basement levels of a parking garage. On the screen, you'll see an Autodesk Inventor created image of our design. We propose a 5-level parking garage with over 300 parking spaces that will be owned and constructed by PSE&G, but leased out to a parking company who will deal with the parking end of the business. On the roof, you'll see these green structures, which are solar carport canopies. They will supply solar power to PSE&G's electric grid. Off to the right, you'll see a black access hatch that is very important to reach the transformers, which are the largest and most difficult to deal with parts of the station. Beside that, there's the control room, which houses the most fragile parts of the station, which must therefore be kept out of the basement and above the flood line. We've also included 5 electric vehicle charging spaces, along with several bike racks, in order to encourage more environmental travel.
In our N-2 design, every component is developed in a set of 3. As you can see on the electrical layout, the electricity enters the substation through 3 transmission lines, 2 current circuits, and 1 feeder line. The electricity then enters the main bus system, which in our case is the breaker and a half, and is then transmitted to the 3 transformers you can see towards the middle. At the transformers, the initial 138 kilovolt voltage is stepped down to 26 kilovolts and 13 kilovolts. And that electricity is then transmitted to the respective feeder rows. The larger feeder row towards the right takes the 26 kilovolt voltage, which is then to be transmitted to the local airport, where the smaller feeder rows you can see towards the bottom take the 13 kilovolt power, which is to be then transmitted to the local community. On the physical layout, you can see how each component was developed using accurate dimensions, proving the feasibility of this compact underground substation layout. We chose to exclude the transmission lines from this diagram in order to provide the best view of each individual component.
One of the biggest challenges we faced when we decided to place our substation underground was what to do with the 3 transformers required in our N-2 redundancy system. Each transformer has a dimension of 15 feet by 20 feet on the base, along with a height of 15 feet, meaning that you need at least 20 feet of clearance just to have a transformer in the substation. Transformers also need to be accessed for maintenance and occasional repair, which added an additional challenge. We managed to put the transformers on the right side of the substation underground, where there is a 20-foot clearance region, and we also installed a access hatch on the right side of the parking garage, so that we can slide the transformers into the hatch and lift them up using a crane if any repairs or replacement is necessary.
Our parking garage design incorporates electric vehicle charging stations. In choosing what station to use, we looked at both smart chargers and dump chargers. Smart chargers are more expensive because the electricity is paid for using a credit card. Dump chargers are cheaper because the user simply plugs in and begins charging. We decided to use a dump charger because our parking lot is a paid lot and we can have users charge for the electricity as they enter the lot. The dump charger we're using is the Clipper Creek LCS 25. It is a level 2 charger, which is a medium charging speed, and is most commonly used in public settings. Level 2 provides 10 to 20 miles of range per hour of charging. Our parking garage includes 5 electric vehicle chargers and wiring for an additional 5 chargers to accommodate the growing number of electric vehicles in the future. In total, this system will cost $13,250.
Safety is important for substations because they transport large amounts of electricity, which can be hazardous if left uncontrolled. To solve this problem, we use the gas-insulated switchgear to keep the electricity within the wires and to conserve space. This also reduces the risk of fires and explosions, both of which have caused problems for oil-insulated equipment. As for flooding, we will install concrete barriers around the basement that block out water. In addition, we will move the fragile control room outside of the parking garage and raise it above the flood level so that if there's a flood, the water will rush underneath and not damage the equipment. We will also implement solar panels to utilize our limited space and to produce alternative energy for the power grid. We will do so by installing solar carport structures, as shown in the bottom image. As you can see, the solar panels are placed on top of the canopy, and they allow for parking below. The solar panels will face south in order to receive the most direct sunlight. On the right, you can see an image of our floor plan on the roof. The green and yellow boxes represent the solar carports, which cover the majority of the roof. We did this in order to maximize the amount of solar energy that can be produced.
In order to determine whether or not our solar project was actually feasible, we had to calculate both the cost and the revenue of the project. The cost is primarily based off the number of kilowatts produced by the solar panels, which in our case is 190.7 kilowatts each year. At a cost of $3,500 per kilowatt produced, the total cost of the project comes out to around $667,000. And because PSE&G is making a green energy investment, they will receive a tax break of about 30% that will bring the cost of the project down to around $467,000. In terms of the revenue, the majority of our calculations were based on the megawatt hours produced by our solar field, which we came out to a value of 228 each year using a PV watts web calculator. PSE&G can profit off of this by both selling the energy and selling SRECs, which are accumulated through the production of power. For the sale of energy, each megawatt hour sold brings PSE&G $50 in revenue, which accumulates $11,000 each year with the 228 megawatt hours. Each SREC, which is a solar renewable energy certificate, is earned through the production of 1 megawatt hour. The SRECs can be sold by PSE&G on their own market for an assumed value of $180 per SREC, and with the 228 SRECs in this project, the total revenue will come out to $40,500. Using both the energy sales and SREC sales, PSE&G would accumulate $52,000 in revenue each year, bringing the break-even point in only about 9 years. For the cost of the parking garage itself, we decided that the cost of construction can be modeled based on the number of spots, with the value being between $20,000 and $25,000 each spot. This data was originally found from Northwestern University and was then confirmed by Richard Franklin, an employee of PSEG Services Corporation. With 364 planned spots in this project, the total cost should come out to around $7.28 million. In terms of the substation itself, a traditional substation has a cost of between $60 and $70 million, but that's for a typical substation, and ours has extra costs to account for. The property must be excavated, and the underground level must also be constructed, which add a total of $4 million into the cost. After adding in the sales tax in New Jersey, the total for the project comes to between a range of $67 to $77 million. There are also many smaller costs in the construction process that we have not accounted for, but they do add up as time goes on, which tells us that the actual cost will be closer to the higher end of our range. And although this does seem like a very large sum of money, it is an investment that PSE&G must be willing to make in order to provide power to its customers. For the cost-benefit analysis of this project, we decided that PSE&G would be in its best scenario by leasing the property to a parking management company rather than trying to manage the parking itself. By formulating a lease agreement with an average value of $272 per spot each month, we decided that the parking garage company can expect an annual profit of 5% each year. PSE&G will receive $1.2 million in revenue from the lease terms, which will then lead to them breaking even on the project after only 6 years. And should the occupancy values of the garage be different than we anticipated, PSE&G will not be affected, but instead the parking garage company will have to adjust its profitability.
Our task was to create a substation that can be placed in an urban area, and we did so by shrinking the dimensions of the substation and placing it underground to conceal its appearance. For safety, we used the gas-insulated switchgear, and we relocated the control room. To benefit the environment, we implemented electric vehicle charging stations and solar panels. Should we continue with this project, we would choose our plot site for the parking garage and finalize the parking structure. In addition, we would negotiate with the parking company and generate a more accurate financial report.
We would like to thank Garen Gunn, supervising engineer at PSE&G, for the countless hours he spent with us teaching us about substations, and for the trip he took with us to Metuchen Switching Station, which really helped us visualize our project.
We would also like to extend our thanks to Nicole Swan, also of PSE&G, for teaching us everything we know about solar energy.
We would also like to thank Wayne Whitman for providing extensive information on electric vehicles, and Richard Franklin and Robert Uni for providing additional input on the feasibility of this project.
We would also like to thank Justin Yu, the supervising RTA for this project, for his dedication in improving our skills in both our research and our presentation.
Lastly, we would like to thank John Patrick Antoine, Eileen Vosen, Rutgers, the State University of New Jersey, Morgan Stanley, NJ Resources, South Jersey Industries, PSE&G, and the GSET alumni community for providing us this great opportunity.
Are there any questions?
they do this as new construction, not as a retrofit for an existing substation?
Yeah, that's right, because it's much easier to go with a plain plot of land so that we can initially install the substation and then have construction on top of it. Because as many parking garages exist now, there's not many suitable clearance levels for getting a transformer or all this large equipment down there, which causes other issues. It just makes it easier. And also PSE&G can then own the property so that if any legal issues come up, it's much easier for them to handle.
And the gas-filled equipment from your pictures looks like that's always an indoor installation rather than outdoor, or is that not the case?
Yes. It's usually housed in a building. So our building would be this underground basement area with the concrete walls.
So did you build that as part of the project? Yeah, do you know what that is actually a picture of?
That's the gas insulated
Which one?
switchgear. This picture?
Yeah.
This is an image of the gas insulated switchgear. Substation.
And this equipment here is manufactured by ADB, which is currently the leading producer of this gas insulated technology. So that's the company we would probably use for this project.
In terms of safety, I noticed that you chose to use a parking garage where people aren't going to be really mostly there during the day, just their cars there. You wouldn't put a daycare center above it, I assume. But I guess my question is, are there any other environmental negative effects of this, electromagnetic pulses or anything else that would mitigate against using it where there's going to be people around?
Okay. Well, that's like another advantage of putting underground was substations also have like other weather impacts that like trees falling down and explosions, fires with the oil that traditional substations use. That like there's other dangers, but since we're implementing gas insulated equipment, that would take away all of those dangers, and putting underground would safeguard the system from the other weather and basically everything other than flooding, which we implemented an additional structure for.
You estimated 9 years for your break-even point for the solar portion of the project. How long do the solar panels last, and how long can we expect to make a profit?
Well, the thing with the solar panels is that they just undergo maintenance whenever there's need for it, and also they don't necessarily turn a corporate profit on the project, but instead they install the solar panels, and then whatever additional revenue they get goes into kind of the system of customers, which takes down their transmission bill.
In the architecture of your substation, where do you anticipate or think about where you would bring in the high voltage retention lines and then 13 kV and 26 kV lines going out as far as the interfaces with the transmission lines?
Well, because this would be in an urban area, the plan for this substation is to have the lines come in from underground, and when the lines reach the outskirts of the city, they'll be raised back down.
Yes.
The transformers is pretty large, and it's pretty heavy. Do you have any plans for how you would go about replacing them?
Well, yes, replacing one, the way we have it set up is the 3 transformers along the rightmost side of the parking garage, and we can move the transformers out into an access hatch along one of the tracks, and then once it gets into that access hatch, a crane can come in to pull it out of the